Hi everyone, and welcome to another episode of Chemistry with Capadia. Today I will be doing a tutorial on how to find the limiting reactant. So to do this, you need to be able to do stoichiometric conversions. So if you are not sure how to do those or you're still struggling with those, you should watch the video on stoichiometric conversions first and then come back here because our focus is going to be on the limiting reactant part of this and not on the conversions part. Okay, so that being said, what is a limiting reactant? So whenever we have a chemical reaction, we have the substances that we're starting with, the reactants, and then we have the stuff that we make, the products. So whenever you have more than one reactant, there's usually significantly more of one thing than another to make sure that everything reacts the way it's supposed to. So the substance that makes the least amount of product is going to be our limiting reactant. Anything that you have left over is the excess reactant. If you only have two reactants, then one is limiting, one is excess. If you have more than two reactants, then you have a limiting and you have multiple excess reactants. There's also a scenario where you don't have a limiting or an excess reactant because both give you the same amount of product. The amount of product that you make is called the theoretical yield. So the theoretical yield is the most amount that you can make given by the least amount that's produced. So if I have enough reactant to make 10 grams of product, but the other reactant I only have enough to make 8 grams of product, I'm only going to end up making 8 grams because after that 8 grams, I run out of one of the things that I need. And you have to have all the reactants in order to make product. All right, so let's look at this problem here. It says, suppose that 32.1 grams of Na2S are added to 8.68 grams of Al to form Al2S3. I'm given a balanced equation here, and then part A says, identify the limiting and excess reactants, and then later we'll get to part B, which says, what is the theoretical yield of Al2S3? So for every limiting reactant problem, instead of the problem telling us one given and one find, we have two givens and one find. So we're going to use 32.1 grams of Na2S to figure out how much Al2S3 I can make. And then we're going to use the 8.68 grams of Al to figure out how much Al2S3 I can make. So I'm going to solve for the same thing, and that will tell me which one of my reactants is going to give me the least amount of product. All right, so we'll start with what we're given. 32.1 grams of Na2S is my first given, and I'm trying to find Al2S3, and since no unit is specified down here either, it just says what is the theoretical yield. I'm going to default to grams. Anytime we are not given a unit for what we're trying to find or our yield, we always default to grams. And then since I am converting from grams of Na2S, I need to find the molar mass. So 1 mole of Na2S is 78.04 grams. And then I'm converting 2 grams of Al2S3, so that means that I need its molar mass as well. So now let's take a look at our problem. So we start with 32.1 grams of Na2S times, if we're starting with grams of Na2S, we need to get rid of grams, so we divide by the molar mass, and then we put 1 mole on top. Next step is mole ratio. So in our equation, I have 3 moles of Na2S, and I'm trying to find Al2S3. Since there's no coefficient, that means I have 1 mole of that. And then lastly, I'm going to convert from moles of Al2S3 into grams, so I multiply by molar mass. So grams Na2S cancel with grams, moles Na2S cancel with moles, moles Al2S3 cancel with moles Al2S3, and I'm left with grams of Al2S3. So this gives me 20.6 grams of Al2S3 from the Na2S. All right, so Na2S produces 20.6 grams of Al2S3. Now, let's look at the other piece of given information, which is 8.68 grams of Al. So I have 8.68 grams of aluminum. And I'm trying to find the same thing. So I have to solve for the same product so I can see which one gives me the least amount of product. All right, so for Al, I will need the molar mass, which is 26.98 grams. And for Al2S3, I already know the molar mass, From the previous one, it's 150.14. All right, so I'm going to set up my problem. 8.68 grams of Al times molar mass on the bottom and 1 mole on top. Then I do my mole ratio. I have 2 moles of Al in my equation, and I already figured out that I have 1 mole of Al2S3. The nice thing is that because we're finding the same thing, the second half of my problem is going to be the same. So I'm solving for Al2S3, so 1 mole goes on the bottom and the molar mass goes on top. Grams cancel with grams, moles cancel with moles, moles cancel with moles again, and I'm left with grams of Al2S3. All right, so when I do this math, I get 24.2 grams of Al2S3 from the Al. Okay, so now I know how much product I get from both of my substances. So I can see here that 20.6 is less than 24.2. So because this value is smaller, the substance that gave me this value is going to be my limiting reactant. So the limiting reactant is Na2S. This is where people make the most mistakes because we look at the smaller number and we say, okay, the limiting reactant is the smaller number. The limiting reactant is not a value, it's a substance. So it's the substance that gave us the smaller number. So we got the smaller number because we reacted 32.1 grams of Na2S. So that's why Na2S is the limiting reactant, which means that Al is going to be my excess reactant because I have Al left over. Once I make 20.6 grams of Al2S3, I don't have any more Na2S left, so the reaction cannot continue, but I'm going to have some aluminum left over because I can't get to 24.2 because I don't have any Na2S. You'll also notice here that even though we started with a larger gram amount of Na2S, it produced a smaller amount of Al2S3. So we can't just look at the values that we're starting with and say, oh, there's less aluminum, so it's going to make less product. That's not always going to be the case because we have to take things into account like molar mass. Na2S has a greater molar mass than Al, so it's going to produce less moles of Na2S. By the same token, we also have to pay attention to our coefficients. I need more moles of Na2S than I do of Al, so overall, it's going to require more Na2S to get me less stuff. All right. Now that we've identified the limiting reactant and the excess reactant, I can look at theoretical yield. So the theoretical yield is the value that is given by the limiting reactant. So basically the smaller value. So 20.6 grams of Al2S3 is smaller than 24.2 grams of Al2S3. So that's going to be my theoretical yield. Okay. So this is just doing stoichiometric conversions, but it's, stoichiometry on steroids is what I like to call it because you're just doing multiple conversions in each problem. So you're just doing more of the same. And then once you've got the conversions, the rest of it is just a matter of looking at which one's smaller and then whatever substance gives you the smaller amount is your limiting reactant and then the smaller amount itself is the theoretical yield. Okay, let's do a couple more. So this says give the limiting reactant, excess reactant, and theoretical yield of Na when 4.75 grams of Al are reacted with 22.7 grams of Na2S. All right, so we are given here two pieces of information. We have the 4.75 grams of Al and the 22.7 grams of Na2S. All right, so let's start with 4.75 grams of Al. And then what are we trying to find? We're trying to find the theoretical yield of Na. So theoretical yield, if we're not given a unit, we default to grams. So we already found the molar mass of aluminum by looking at the periodic table. And then the molar mass of Na, we can do the same thing. We look at the periodic table and we get those values. All right, so now we set up our problem. 4.75 grams of Al times molar mass on the bottom to get grams to cancel, 1 mole of Al on top. Then we do our mole ratio. I have 2 moles of Al on the bottom and I'm finding Na, so I have 6 moles of Na on top. And then lastly, I'm going to convert moles of Na into grams, so I put 22.99 grams on top. So grams Al cancel with grams, moles Al cancel with moles, moles Na cancel with moles Na, and I'm left with grams of Na. All right, so when I do this math, I get 12.1 grams of Na from the aluminum. All right, now let's do the second one, which is 22.7 grams of Na2S. And I'm still trying to find grams of Na. So I'll need molar mass Na2S, which is the same as it was in the previous problem, 78.04 grams. And the molar mass of sodium is the same as it was above as well. So start with what we're given, 22.7 grams Na2S times, divide by molar mass, 78.04 grams Na2S, 1 mole Na2S on top. Then we do mole ratio, 3 moles Na2S on the bottom. And then we're finding Na, so that's the same as the previous problem, 6 moles Na on top. And then lastly, we convert to grams. We do 22.99 grams of Na over 1 mole of Na. Grams cancel with grams, moles cancel with moles, moles Na cancel moles Na, and I'm left with grams of Na. So when I do this, I get 13.4 grams of Na from Na2S. Okay, so I've done both of my conversions. I get 12.1 grams and 13.4. 12.1 grams is the smaller value. So the 12.1 grams is going to be my theoretical yield. 12.1 grams of Na is the theoretical yield because it's the smaller value. The limiting reactant is going to be aluminum because Al is what produced the 12.1 grams. And then Na2S produced the bigger number, so the excess reactant here is going to be Na2S. So the Lr is Al, the Er is Na2S, and the Ty theoretical yield is 12.1 grams of Na. Okay, so let's look at another. This says identify the limiting reactant and give the theoretical yield of Cr2S3 when 14.2 grams of CrOH3 are reacted with 7.04 grams of H2S. So we have a brand new equation here. It's already balanced, so I don't have to worry about that. All right, so I'm given 14.2 grams of CrOH3, and I am given 7.04 grams of H2S, and I'm asked to find the theoretical yield of Cr2S3. All right, so we'll start with the first piece of information we're given, 14.2 grams of CrOH3. And since we're not given units for a theoretical yield, I will default to grams of Cr2S3. All right, I'm going to need the molar mass because I'm just doing all grams all the time, 103.3 grams. And the molar mass of Cr2S3 is going to be 200.18 grams. Now we have everything we need to solve our problem. 14.2 grams of CrOH3 is what we're given, so it's what we start with. Divide by molar mass, 103.3 grams with 1 mole on top. And then we do mole ratio. CrOH3 has a 2 in front of it, so we'll put that on the bottom. And Cr2S3 has no coefficient, so that means it's just 1. And then we will convert from moles into grams, so we multiply by the molar mass of Cr2S3, which is 200.18. Right, grams cancel with grams, moles cancel with moles, moles cancel with moles, and I am left with grams of Cr2S3. So 14.2 times 200.18 divided by 103.03 divided by 2 gives me 13.8 grams of Cr2S3 from CrOH3. All right, now let's do the second one. we have 7.04 grams of H2S. We're still trying to find grams of Cr2S3. So we'll need both molar masses again. So the molar mass of H2S is going to be 34.08 grams H2S. And the molar mass of Cr2S3 is the same as above. All right, so let's set up our problem. We're starting with 7.04 grams H2S. So we divide by molar mass and 1 mole H2S on top. Then we do mole ratio, 3 moles H2S, and still 1 mole of Cr2S3. And lastly, we convert to grams, 1 mole Cr2S3 on the bottom, and the molar mass on top. All right, so grams cancel with grams, moles cancel with moles, moles cancel with moles, and I'm left with grams of Cr2S3. And when I do this math, I get 13.8 grams of Cr2S3 from the H2S. All right, so this is a unique situation. Both reactants give me exactly the same amount of product, so there's no limiting reactant. Nothing is limiting how much I make. I have exactly enough to make 13.8 grams regardless. So there's no limiting reactant, and my theoretical yield is just the 13.8 grams of Cr2S3. All right, so both substances can make the 13.8, so 13.8 grams is my theoretical yield. For some reason, if we ever see these numbers together, people are tempted to add them together. Don't do that. It's one or the other, and since these are the same, it's just that number. Okay, so let's do a few more. This says how much H2O is produced from the reaction of 20 grams of CrOH3 and 20 liters of H2S at STP. What is the limiting reactant? All right, so it's the same thing. I've got two givens, 20.0 grams of CrOH3 and 20.0 liters of H2S. This is the first time that we've seen a unit other than grams. It doesn't make any difference at all. We're still doing the stoichiometric conversions. We still have these molar conversions to choose from, so it's all going to be fine. And then we are asked how much H2O. Since it doesn't specify the amount of H2O, we are going to revert to grams. So if it just says how much of something are you making, you're looking for the theoretical yield. Okay, so we're starting with 20 grams of CrOH3, and we're trying to find grams of H2O. Right, so 1 mole is equal to 103.03 grams of CrOH3. And then we need the molar mass of H2O as well, which is 18.02 grams of H2O. All right, so we start with 20 grams of CrOH3 times molar mass on the bottom, 1 mole on top. All right, then we do mole ratio, 2 moles CrOH3 on the bottom, and we're finding H2O, so 6 moles H2O on top. And then lastly, we convert from moles to grams, so we put the molar mass of H2O on top. Grams cancel with grams, moles cancel with moles, moles cancel with moles, and I'm left with grams of H2O. So this produces 10.5 grams of H2O from the CrOH3. Now let's look at the second one. Here we are given 20 liters of H2S, and we're still trying to find grams of H2O. All right, since we're given liters, I need the liter conversion, which is going to be 1 mole is equal to 22.4 liters. It's 22.4 liters at STP, and we can see here that we are at STP, so that's all. It's all good. And then our find is the same. We still need the molar mass of water. All right, so now let's do our conversion. 20 liters of H2S is what we're given. So we get rid of liters by putting 22.4 liters in the denominator, and that's going to be 1 mole. And then I look at my equation. There's 3 moles of H2S, put that on the bottom, and there's still 6 moles of H2O. And then lastly, I convert 2 grams by multiplying by 18.02 grams of H2O. So liters cancel with liters, moles cancel with moles, moles cancel with moles again, and I'm left with grams of H2O. All right, and then when I do this math, I get 32.2 grams of H2O from H2S. So I have 10.5 and 32.2, so 10.5 is the smaller number. So that means that my theoretical yield is 10.5 grams of H2O. And my limiting reactant is what gives me the theoretical yield. So that is going to be CrOH3. All right, let's do one more. So this says how many particles of Cr2S3 can be made from 3.6 moles of H2S and 8.7 moles of CrOH3. All right, so there's a couple different things here. I still have 2 givens. Both my givens are in moles, which is fine. It means that I just don't have to convert from something to moles, so I don't need my first conversion factor. And then I'm trying to find particles of Cr2S3, which is different from before because before it didn't give me a unit, so I just used grams, but here it's giving me particles, so I'm going to need to use the particle conversion, which is 1 mole is equal to 6.02 times 10 to the 23rd RPs. Start the same way. First given is 3.6 moles of H2S, and I need to find particles, which are RPs of Cr2S3. So since I'm already in moles, I'm not going to need a conversion factor for this, but I do need a conversion factor for RPs. It's going to be 6.02 times 10 to the 23rd RPs. So now we'll set up our problem. 3.6 moles of H2S times, all right, so since I'm already starting with moles, I can just go right to the mole ratio. So I have 3 moles H2S on the bottom, and I'm converting to Cr2S3, so 1 mole Cr2S3 on top. And then I need to convert moles into particles, so I'll do 1 mole Cr2S3 on the bottom, and 6.02 times 10 to the 23rd RPs, Cr2S3 on top. All right, so moles H2S cancel with moles, moles Cr2S3 cancel with moles, and I'm left with RPs of Cr2S3. And when we do this math, I get 7.2 times 10 to the 23rd RPs Cr2S3 from H2S. And then the second given is 8.7 moles CrOH3. And my find is the same, RPs Cr2S3. Again, since I'm starting with moles, I don't need a conversion factor, but for RPs, I do need 6.02 times 10 to the 23rd RPs. So now let's plug in. I start with 8.7 moles of CrOH3. So since I'm starting with moles, jump right into mole ratio. So 2 moles CrOH3 on the bottom, and then 1 mole Cr2S3 on top, and then same as above, 1 mole Cr2S3 on the bottom, and 6.02 times 10 to the 23rd particles on top. All right, and when I do this math, I get 2.6 times 10 to the 24th RPs Cr2S3 from CrOH3. So now I do the same thing as before. It's whatever number is smaller, 7.2 times 10 to the 23rd versus 2.6 times 10 to the 24th. So even though 2.6 is smaller than 7.2, the 24th is a larger power than 23. So the 23 is going to be smaller. So that means that my theoretical yield is 7.2 times 10 to the 23rd RPs of Cr2S3. This doesn't ask us for limiting reactant, but if it did, H2S would be my limiting reactant. All right, so that is limiting reactant. We just, do our stoichiometric conversions multiple times, pick the smallest one, and we are good. This has been another episode of Chemistry with Wikipedia Tutorial Edition. I hope you learned something, and until next time, keep on chemin'.